Hi, everyone. Welcome to part 2 of lecture number 13. So we have 3 more examples to cover now. One more example from tutorial 13A and then 2 from tutorial 13B. So I just wanted to remind you at the start of the tutorial is this list of tips for solving dynamics problems. And you'll see that for all of the problems that are coming up, I'm going to be following this sort of same sort of method right here over and over again. I want to point out a couple quick things before we dive into these examples, the remaining examples. And first, I just wanted to point out how you'll notice that for each of the problems that we've solved so far, the only formula of physics that we memorized and keep using is Newton's second law, which is this one right here. Okay, either for x components or y components or for the full vectors. But what we do not memorize and simply recall is, for example, the relationship between tension in a rope and acceleration for an object that's suspended from a rope. Instead, we derived it from scratch for this object. And why is that? Well, because that's not a fundamental formula of physics. It is specific to this particular example. And it'd be very easy for us to simply have a second rope pulling upward. So there are two tensions, and then all of a sudden this equation is no longer correct because now we have one more force that we would need to add over here in our inventory of forces, and then the left-hand side of this equation would change. The same thing goes for the piano in problem 2 that we did. Um, all we'd have to do is simply add in some friction or something on the horizontal surface, and then there'd be another force here, and then this would no longer be a true statement. Or one of these people would have to push in a diagonal direction, either downward or upward, and then all of a sudden there would be a y component in this expression here, and this would no longer be a true statement. So we don't bother to memorize these derived results for specific cases, unless it's a really common case. Then you might accidentally memorize it or just want to know it. What we do remember is Newton's second law. That is the general fundamental formula of physics. And then all of this other stuff here with free body diagrams and defining our axes and decomposing forces in this inventory list right here is just in the service of plugging things into Newton's second law, right? And deciding how, and in other words, I'm sorry, getting together all the things that we need to put into the left-hand side of this equation. That's really all this is. The last thing I wanted to mention before we actually start example 6 is something that I said at the end of part 1 or near the end of part 1, and that is when we have objects that are either stuck together or connected, in this case by a taut inelastic cord. So that means that this cord doesn't stretch like a spring. Then the motion of object 1, the motion of object 2, and the motion of the system, M1 and M2 sort of as a whole, the system of masses, will all be identical. And I'm using motion here loosely to mean the acceleration, the velocity, and the displacement of those of mass 1, velocity, acceleration, displacement, mass 2, and velocity, acceleration, and displacement of the system are all exactly the same. So you'll see that in this example that I'm about to start, we don't need to write a subscript on the acceleration and the velocity to specify, oh, the a sub 1 is the acceleration of mass 1 and a sub 2 is the acceleration of mass 2. You could do that if you want, but part of solving this problem will be to realize that those are equal. So I'm just going to go ahead in this case and make that realization up front, and then I can just use A. A will be the acceleration of either mass 1 or mass 2 or the system of the masses, and it's all the same at all times. Okay, so in that case, let's go ahead and make a prediction here. We're given the masses of the two boxes. We're told that there is a force, maybe from a person over here, or so just any outside applied force. That it is there's a force applied to the right-hand side of box 2, and then we're asked ultimately down here to find the acceleration of the pair of boxes, which in other words it's the same as the acceleration of either box, and to find the tension in this connecting cord in between the two. Okay, so let's make a prediction up front about how the tension in this connecting cord is going to compare to this force Fp that's applied on the right-hand side. Well, initially, you might think, oh, Newton's third law or something like that would cause, if this is 10 newtons on the right-hand side, then the box must pull on this, let's suppose this is a person. The person pulls on the box with 10 newtons, the box pulls on the person with 10 newtons, and then this box must pull on the cord with 10 newtons and 10 newtons and 10 newtons all the way down the chain. Well, that wouldn't be, I mean, that first part of what I just said is correct. If the person pulls on box 2 with 10 newtons, box 2 pulls on the person also with 10 newtons at the same time. But it turns out there's no reason then why, if the box 2 is pulling on the person with 10 newtons, that box 2 must then also pull on this cord with 10 newtons, because that's not a Newton's third law pair. And in fact, it doesn't. Let's think about what these forces doing. This 10 Newton force here needs to accelerate the entire two box system to the right at some acceleration. The tension in the cord only needs to accelerate box 1 because everything is being pulled to the right. So the tension in the cord only has to accelerate box 1 at that same acceleration. So we know that force is equal to mass times acceleration. So if 10 newtons is accelerating this very large double mass at the same acceleration as the tension force in the connecting cable is accelerating only one mass, then it would make sense that this force in the connecting cable will be a lot smaller. Okay? And that's that's my prediction, that it will be less than 10 newtons. Okay, and it looks like if this is 35 kilograms and that's 22 kilograms, maybe 60% of the mass of the system is in M1. So I'm going to just guesstimate that the tension in this connecting cord is probably around 60% as much as FP. So maybe 6 newtons, something in that ballpark. All right, let's go ahead and create free body diagrams for M1, M2, and the system, just for the practice of doing it. We're not probably going to use every one of those free body diagrams. Okay, so what I'm going to do is I'll start with, let's see, what's the best way to arrange this here. Okay, I guess what I'll do is I'll start with the system over here. Okay, and this is going to be the system of both masses. So really, there's the right-hand side and the connecting cord, but I'm just going to draw it like one really big mass. In a lot of textbooks, they would call this capital M. I'm just going to call it M total. So this is M total, which is equal to M1 plus M2. Okay, and remember what a free body diagram has to do. Okay, so this is what we're doing. We're doing the free body diagrams down here. It has to illustrate all of the external forces acting on this system. So we know that the Earth pulls downward with gravitational weight. So there's a really big weight, which I'll call weight total, right? Again, you can call these W if you want. There's a normal force from the surface pushing up on the pair. I'll call that F sub n tot. And the reason I'm adding the total subscript is because I want to distinguish that from the weight and the normal force for the other individual boxes. Okay. And then the only other external force acting on the system of the two boxes, remember, we're treating this as a single object, right, is FP, maybe the person, or whatever that external force is, pulling to the right. Would I have the tension from the internal cord? No, because that is not an external force. That'll be an internal force, and all internal forces always sum up to 0 because of Newton's third law. On the other hand, what if I were going to just do a free body diagram of just M2? I want to leave enough room between these that I won't, or just F1. I don't want to collide my drawings. Okay, so this is just M1, this is just M2, and this again is the sum of the two boxes, the system. This is the entire system. Okay, if we just draw the free body diagram for M2 alone, it has its own smaller weight, which I'll call Fg. And you know what? I'll put these on both of these. M1 has a weight, Fg1. Okay. Okay, well, comma, it doesn't matter. There's a normal force acting on both of these, Fn1, Fn2. And then there are cables. So there's the tension on box 1, there's the tension from the connecting cable that pulls to the right. If that's the only tension in the problem, then we'll call it Ft, or just capital T if you want, right? Because Fp is labeled with a distinct name that's different. And that's it. So for box number 1, our free body diagram is now complete. There are no other external forces acting on box 1. How about for box 2 right here? It turns out there's 2 external forces. There's the tension in the connecting cable. Remember, the tension in a cable pulls inward from on both of the ends of the cable. It's the same for an ideal cable that's massless, and for an ideal cable that's massless, the tension is the same at all points along the cable, and it pulls inward from both of its ends. It's just like a spring would as well. And then on the right-hand side of box 2, there is Fp pulling to the right. Okay, so notice the free body diagram for mass 1 is different than for mass 2, right? The weight and the normal force are different, but most importantly, on the horizontal direction, the forces are really different. These two forces have the same magnitude, but notice how their directions are opposite, because the cord pulls box 1 to the right and it pulls on box 2 to the left. The system excludes Ft. So if I go ahead and inventory these forces, if I go ahead and decompose these forces into components, I'll try and do this fast, just by inspection. No trigonometry needed. Okay. Okay, so forces. All right. So if we just did box 1, box M1, okay? Then we have the normal force, whose magnitude we don't know, points upward. The weight, whose magnitude we do know, and it points downward. And then this tension to the right. The entire magnitude points in the positive x direction, and that's it. So now, which of these sets of forces would we use? Well, it depends on whether we're going to apply Newton's second law to just box M1, just box M2, or to the system of the two. This is going to look a lot alike, although these are different magnitudes, different sizes, different numbers of newtons. This is the weight of box 2. The connecting cord this time pulls in the negative x direction, and the person is pulling on the right-hand side in the positive x direction. So there's 4 forces acting on box 2. And then finally, for the system, this is a little bit of overkill because we're not going to use a lot of these forces. But I want to just show you the complete thorough method because there are problems and cases where you would want to use all of them. So that's the weight of the whole system. Okay. All right. So now the last step of a dynamics problem is to then apply Newton's second law. And if we wanted to, we could apply Newton's second law in the horizontal direction and the vertical direction to each of these objects. Now we will get, so that would give us 6 equations, right? However, that will give us some redundant information and some sort of trivial information that we don't need. So let's tailor our approach a little bit to what the question is actually asking. We're asked to find the acceleration of the pair of boxes, which, by the way, would be the same as finding the acceleration of either box alone. So all those options are available to us. It's a matter of knowing using what we are given and avoiding things that are still unknown. And then the second thing we're asked to do is to find the tension in the connecting cord. Okay, so the acceleration of either box will appear in any of those Newton's second law expressions. It'll be the acceleration on the right-hand side. It'll be the same. And then there's a tension in the connecting cord, which shows up here and here. So it would be in the Newton's second law for either box 1 alone or box 2 alone. Well, given that we know the masses g and the magnitude of Fp, I think we can get the acceleration of either box from that system equation on the right-hand side. So let's do that. Let's find the acceleration of the system. So we're going to apply Newton's second law. And the system accelerates in the horizontal direction. So I'm going to take the sum of the forces in the horizontal direction, apply Newton's second law in the horizontal direction. And this is the system of masses. Right? And now I get just the horizontal components of these forces, and notice it's 0, 0, 0, and Fp. So 0, 0, and Fp. And that's it. 10 newtons. The sum of the two masses. And that looks like, this looks like 57 kilograms for M total. And that means that that means that the acceleration of the system in the horizontal direction is going to be equal to 10 divided by 57. And my calculator tells me that that's equal to 0.1754 meters per second squared. Now, if this is a 3 sig figs problem, then I guess I'll round that 3 sig figs. And it's exactly to the right. Right, the x component is positive. We know there's no y. Y sub y is 0 because these are all sliding on a horizontal surface. So the y direction there is no motion at all. So a sub y is 0, and velocity and displacement in the y direction are all 0. Now we're almost done. To find the tension in the connecting cord, how can we do that? Okay. Well, it looks like we have two options. I'm going to get a clean sheet of paper here. Okay. Now that we know the acceleration of the system, okay, then if I were to apply Newton's second law to just box 1 alone in the horizontal direction, I could use the same acceleration as we found here for the system, and we know that's also the acceleration of box 1, and that should work. So I'm going to just cover this a little bit here. Okay, so finding to find the tension in the connecting cord, let's apply Newton's second law. To M1, okay? And we're going to do the horizontal direction. And now I'm going to add up these horizontal components here. And there's the tension in the connecting cord, which is what I'm after. Box 1 has a mass of 35 kilograms. And the acceleration that we had in the previous part is 0.1754. And I'm going to keep an extra sig fig here for the moment. And then that turns out, I asked my calculator what that is, and it's 6.140 newtons. Okay, rounding to 3 sig figs. Great. So we were right. It is less than 10 newtons. Okay, because all it has to do is just accelerate one of the two masses, whereas Fp has to accelerate both of the masses at the same acceleration. So it has to be a stronger force. It turns out, what if I had instead applied Newton's second law to mass 2? So sometimes there's more than one way to proceed. Let's find out. I'm going to cover my answer from before, and I'm going to say, okay, let's apply Newton's second law to mass 2. sum all of the x components of all the forces right here, 0 plus negative tension magnitude plus Fp is equal to m2 times acceleration. That's the same acceleration as we just used before, because the system in box 2 and box 1 all have the same acceleration. So the tension in the connecting cord, remember, make sure you use the correct mass. Notice how I've been really careful to put subscripts on every m, on every mass. And especially when it's a sum, you have to either spell it out or you have to rename it m tote or something like that. All right, so it looks like the tension in the connecting cord is going to be 6.140 newtons again. Now, technically, what we've just found here is the tension pulling to the left on mass 2, whereas before, what we saw for before was the tension pulling to the right on mass 1. So they're the same, right? And that's the way it should be for an ideal cord. An ideal cord should pull inward on both of its ends with the same tension. Okay, all right, good. Okay, let's move on to tutorial 13b, and I'm going to solve problem 1 and problem 3 as examples. So problem 1, oh, let me focus. Okay, here we go. So problem 1 shows a heavy crate of known mass, and this is a top view looking down from above, so it's a bird's eye view. And 2 workers pull on this heavy crate with 2 force vectors that are given here. Okay, we're given the magnitudes and the directions. All right, so we're given all the information about the applied forces from the people. Okay, if this crate is on a frictionless surface, then what will be its resulting acceleration? All right. So the acceleration looks like it'll be in the xy plane. Looks like both of these forces are in the plane of the page. So this is pretty much a free body diagram. It's pretty much ready to go. There are 2 more forces I could think of acting on this crate that are not drawn here. There's the weight, which is into the page, and then there's the normal force from the floor, which is out of the page. So in physics 152, we're going to learn special symbols for drawing vectors that are into the page and out of the page, because we'll need that for 3-dimensional problems in physics 152. But for now, I'm just going to ignore those forces, right? For our purposes, those lie in the z direction. What I'm going to do is I'm going to say, okay, let's choose our axes here. So this is the y-axis, and that is the x-axis. So I could have drawn this off to the side, but I just go ahead and put it right on top of the problem here. Okay. And so then the weight and the normal force both lie exactly in the z direction. And looking at this problem, right, these forces have no z components to them. And the floor is, I think, assumed to be flat and basically flat in the plane of the page, or parallel to the plane of the page. So I think that the weight and the normal force are going to exactly cancel each other out. And I'm not asked to calculate what that is, so that's fine. We'll just omit it then from this problem. All right, so now my free body diagram is basically complete. I've chosen my axis directions. So now I can decompose my forces into their components if I wish, or I can just go ahead and think about this in terms of Newton's second law from the full vector form of the equation. So remember, the component method is pretty much the foolproof method that always works in all cases. So if we wanted to, I could then write out and find F1 and F2 in components and do that now. And then combine, and then apply Newton's second law to the X components, and then apply Newton's second law to the Y components separately. I think what I'm going to do though is, well, yeah, I'll follow the solution that's it. You know what? I'll tell you what. Instead of following the solution that I've uploaded, what I'll do is I will show that slightly different variation. Okay. And we'll go ahead and do the components in the x direction and the components in the y direction, and then we can recombine that at the end. Okay, and that will work. That'll also work. Okay, so let's decompose these into their components. So once again, this as a whole, this will be a slightly different method than what is on my written solution, but that's good. That way you'll see another one. You'll see a slightly different method that still leads to the same answer. Okay, so F1. Okay, we know that in order to get the x component of any force, well, actually F1, we can pretty much do it by inspection, right? So let's just do that. F1, we can see that the entire magnitude lies in the negative x direction, and it's 450 newtons. And it has no y component at all. And then F2, all right, we're going to have to do a little trig here. The x component is magnitude times cosine of the trig direction. And in this case, the trig direction is 315 degrees, right? It's all the way around. And then I ask my calculator what this is. And in these two cases, this is positive 459.6 newtons and negative 459.6 newtons. Okay. All right, so and that's what we would expect for something that's on one of these exact 45-degree directions, exact diagonals. Okay, now we can go ahead and say, great. Now we know what F1x is, F1y, F2x, F2y. That's all of our forces and components. So now we can apply Newton's second law. So this is where I'm going to diverge from my uploaded solutions a little bit. We'll apply Newton's second law now. Horizontal and vertical. And what this will do is it'll allow us to find the acceleration horizontal component and acceleration vertical component. Okay. Now yeah. All right. Let's go ahead and proceed, and then I'll make a comment at that point. Oops. Sum of all the horizontal components. And the object of interest, the mass of interest, of course, is just the big crate. Okay, that's the mass m. So this will be F1x plus F2x. So we're adding up those components just to write things out a little formally. Okay, and then I need to ask my calculator what that is. And this is actually a relatively small number because it just so happens that the final acceleration, the net force and the final acceleration is very close to the vertical axis. So the horizontal component is actually very small. Now you never need to write the plus sign. Sometimes I just do it for emphasis. All right, now let's do the same thing with the vertical components. Then the vertical components. much, much larger. Okay. All right. So the problem is asking us for the acceleration of the crate, magnitude, and direction. So at this point, we have found the acceleration of the crate, right? The acceleration of the crate in the XY plane is this, right? The only problem is we just have it in components when the problem is asking us for magnitude and direction. So now let's find the magnitude and direction of this acceleration vector. Remember the magnitude you get with that sort of Pythagorean theorem looking expression like that. Oops. Notice I use a lot of parentheses to really make it clear that the square applies to everything, the units and the value. And when I ask my calculator what this is, I get 0.6130 meters per second, okay? So notice adding this to that squared just barely changes the value. Now for 3 sig figs, this will round down. So I'll do that in just a moment when I write my final answer. So that's the magnitude. So notice when I write A without the vector hat, that's the magnitude. There's no subscripts on it, right? Those would be the components. And when I put the vector hat on top, that means here is the entire vector, either in components or magnitude and direction. Oops. The direction is going to be the inverse tangent of the y component over the x component. I asked my calculator what that is, and it tells me the answer is 88.8 degrees, negative, pardon me, 88.8. But I know that there's actually a second solution on the unit circle as well that's 180 degrees away. So I add 180 and I get the alternative solution, and then I have to choose one because they're not both physically correct. Okay, well, how do I decide which quadrant I want? Well, one way to do it is to look at, if I don't have a drawing or a sketch of the vector, is to look at the signs on the two components. It looks like both of the components have positive signs. So, oops, that's a mistake. Pardon me. The y component should be negative. I must have been trying to write and talk at the same time. Okay. So that doesn't change the fact that the magnitude here is still positive, but it's supposed to be negative there. Inverse tangent, great. Okay, good. Okay, so now, pardon me, where was I? All right, so now I look at this and I see that I have positive x component and negative y component, and I know that that lies down here in the fourth quadrant. So I'm going to choose the one of these that is in the fourth quadrant, and I'm going to discard the one that's in the second quadrant. That's it. So therefore, the acceleration vector is 0.613 meters per second squared magnitude at a direction of negative 88.8 degrees. Trig angle. And it'd be nice before we leave this problem completely to just do a quick little sanity check and ask ourselves, look, we know the acceleration is supposed to be in the same direction as the net vector, as the sum of these two vectors. So if I just do a quick sort of tip to tail addition, let me just do that right here, okay? I'm going to pick up F2 and put it at the end of F1. Okay, well, the problem is these are not drawn to scale. Okay, F1 is only 450 newtons and F2 is 650. So let me shorten F1 to what it should be. Okay, all right, so now F1, if this is 450, 650, that looks a little closer. All right, so now if I put F2 at the tip to tail at the end of F1, I should get something that looks like this. All right. So now the sum of F1 plus F2, or F tot, should be from the start of F1 to the end of F2. So that's F total. And therefore, acceleration, actually, you know what I'm going to do? Yeah, I'll just get another color. And we know from Newton's second law that acceleration has to be in the same direction as the net force vector. So if the net force vector lies down here in this direction, fourth quadrant close to the negative y direction, so does the acceleration. 1 over m is just a scalar. It's a positive scalar. So the acceleration has to lie in exactly the same direction as the direction of the total force vector, right? And that makes sense because it's the net force that gives rise to acceleration. So if net force points at negative 88 degrees, the acceleration will be at negative 88.8 degrees as well. All right, that's good. So just doing this little sketch here shows me that the direction we got of negative 88.8 looks reasonable based on the geometry of this problem. I'm sorry that original sketch was, the original diagram was so inaccurate. All right, so that's number 1. Now we're going to switch to number 3. Oh, but I'll leave number 2 to you as an exercise, and number 2 has a lot in common with number 1. So that's why my intention is that it will reinforce number 1. And the same is true for problems 3 and 4. Problem 4 has a lot in common with problem 3. So problem 3 here, this is now a side view of a box resting on a horizontal floor. Okay, and suppose it has a strap or a handle or something that allows a person to apply a force here at an angle of 30 degrees above the horizontal. So it looks like, oh, that's actually a trig direction if we choose our axes to be, now we're going to choose our axes to be along the direction of motion, okay? So let's choose a positive x direction to be in the direction that the suitcase is going to, the box is going to accelerate. And let's choose the y direction must be perpendicular to it. Let's choose it perpendicular to the floor. Okay, so positive x is parallel to the floor in the direction of motion, and positive y will be perpendicular to the floor. So that means normal force will and weight will be exactly in the y direction, and motion will be exactly in the x direction. That makes our math easier. All right, so we're given the magnitude and the direction of this applied force here. We're given the mass of the box, 10 kilograms, right? So this is the mass of the box. That's the magnitude of the person's force. That's the direction of the person's force. Great. And now we're asked to find the acceleration of the box and the normal force from the floor. All right, let's follow the same steps as before. So I'm going to create a free body diagram. Oh, first of all, identify the mass. That's easy in this case. It's just a box. Now let's construct a free body diagram of the box and identify all of the external forces that are acting on the box. Okay. So the box has weight, the gravitational force of the Earth. There's a normal force from the floor. Okay. And then there's the person's pulling force, like this, which we know, actually this, I could have just used that. I could have just used this diagram up here to form the free body diagram, but okay. So the person's pulling force is at an angle of theta p above the horizontal. All right. We've chosen our axes, right? And we've inventoried all of the external forces in the box. There's no friction, frictionless floor. So now let's write these, decompose these into their components. All right, just by inspection, we can see that the normal force has no horizontal component. And what is the magnitude of its vertical component? We don't know. Once again, tension and normal force don't have a formula that always works all the time. And so unless it's given to us in the problem, which it's not, in fact, it is an unknown. So all we can do is just write its magnitude as an unknown. All we know is that it lies exactly in the positive y direction. On the other hand, weight lies exactly in the negative y direction, and its value is always known. It's always, regardless of the motion of the box, the weight will always have a magnitude of m times g in the negative y direction. Finally, the person Fp decomposes into Fpx, so this is the x component, and Fpy, right? As long as theta is the trig direction, then this works. All right, great. That's done. So now, last step, apply Newton's second law. This time, the vertical direction is not going to be quite as boring as it is for some of the other problems, because the person's pulling force here has a vertical component, right? So I don't know. Sometimes it matters what order you do these, or sometimes you have to do the two simultaneously because there'll be two equations with the same two unknowns. In this case, let's just work on the horizontal one first, see where it leads, and then move over to the vertical one. Sometimes one of the two will basically be lead to a dead end until you do the other one. Sometimes one of them will be totally uninteresting and give you something like 0 equals 0 and not help. All right, so sum all the horizontal components of all the forces. Looking down the list, that's 0 plus 0 plus Fpx. All right. Well, you know what? Let me do a little progress on the vertical one just so I can make a point about this. Adding up all the y components of all the forces, this has a lot more going on this side. Y component of normal force, y component of weight, y component of the person's pulling force, where this is the magnitude, so that's a positive quantity. And then if theta were positive or negative, this, or depending on the value of theta, this could be positive or negative. Okay, but this is the magnitude, so it's always positive. Now, if the box doesn't leave the floor, then we know that the acceleration, velocity, and displacement in the y direction are always going to be 0 at all times. In other words, if the box slides along the floor, then that means its motion is only in the x direction and has no y motion at all. So we can then say that this must be 0 because the box stays on the floor. Now, it could be that if as we solve this, if we could make the value of Fp so large that it will exceed the weight, that Fp sine theta will exceed the weight, and then the box would actually leave the floor. That would be, imagine the person pulling so hard here that the box would just sail off the floor, right? But I think in this we would find that out because we would get some sort of weird, absurd answer like a negative value for the magnitude of the normal force here. And then we would know that, oh, that's not physical. And that's because the scenario has now changed, right? Once the box leaves the floor, the normal force goes to 0 and the free body diagram changes. But in this case, that I doubt that's going to happen, right? The person's pulling force is only 40 newtons. We know just at a glance that the box's weight is 98 newtons. So, yeah, not likely. All right. So, it looks like when part B is asking us for the box's acceleration, all of that action happens over here in the horizontal direction and not in the vertical direction. So let's go ahead and finish solving the horizontal equation. And everything else is known, and we can solve for the acceleration. And then I get that the acceleration x component is 3.464 meters per second squared. Now that's an extra sig fig for now, just in case we needed it for anything, but I don't think we do. It looks like it's positive, so that means that the x component of the acceleration, let's say that the acceleration vector is approximately 3.46 to the right. X component is positive, so therefore the direction of the whole vector is to the right. There's no vertical component, right? A sub y is 0. All right, so that's part B. Part C, the normal force lives over here. And it looks like in this particular problem, we know everything else. Everything else is given. So let's go ahead and solve for the normal force. I'm just going to collect things on the other side of the equation. And the reason I wanted to do that is it tells me something, right? What is the equation saying to us here? It's saying the magnitude of the normal force coming out of the floor is going to be equal to the weight of the object, mg in magnitude, less the upward component, fp sub y, right? This is the upward component here. So it's fpy of the person's pulling force, right? If the person had no upward component to their pull, then the normal force would just be equal and opposite to the weight. It would counteract the weight exactly, and it'd be mg. But the person is slightly, the person is lifting the box, not physically through the air, but is lifting the box away from the floor just a little bit. So what happens is the box's weight doesn't change. The normal force from the floor begins to lessen to compensate for that. So that way, the sum of all the forces in the vertical direction still sums to 0. In other words, this is dynamic equilibrium in the vertical direction. The way that happens is the normal force from the floor gets less and less and less. Think of this another way. If this box were on a top of a scale, and that scale was on a frictionless little wheels, then what would the reading on the scale become as the person's upward pulling force becomes, let's say, more and more vertical or stronger and stronger? Well, we would expect that the scale reading would gradually diminish, and that's because the normal force coming out of the floor, right, which is what the scale tells you, is getting smaller and smaller. Conversely, if a person had a downward pushing force like this, then we'd expect the reading on the scale, that the normal force from the floor has to get bigger and bigger to counteract both the weight and the downward component of the person's pushing force. And if it were sitting on a scale, we would see the reading on the scale get bigger and bigger. Okay, so let's go ahead and solve the problem. The weight of the box is 98 newtons. And here's the vertical component of the person's pulling force in this case, which is exactly 20 newtons. So it turns out the magnitude of the normal force in this case is the weight of the box less this little upward component of the person's pulling force, 78 newtons. So in problem 4, problem 4 is a very similar example, but it has the person pushing with a downward component. So we would expect in that case the normal force from the floor to be greater than just the weight of the box. And if the person were to push exactly horizontally, like all of the people piano in tutorial 13, I'm sorry, in the sample problem A, in that case the normal force from around is exactly equal and opposite to the weight, just mg. All right, so that concludes the sample problems for this part. I forgot to say this at the start, but of course, in the future, if you already know how to do these, or if you'd rather just look at my solutions instead of listening and watching me work through them, then please do, right? Feel free to use that instead of the lecture. During the lecture, I try and tell you when I'm just going to be doing sample problems instead of covering any more theory. So no need to listen and watch me this whole time. Feel free to skip ahead, or feel free to just look at the written solutions. So this is, I'll just end here with a little reminder that online homework, it's called online homework 13 through 15. It's a relatively short assignment, though. It's only about 9 or 10 problems, and the first half of it is just a few dynamics problems. mostly one-dimensional with just a single two-dimensional. So go ahead and try those now.